All right, so starting off with a few announcements, reminders, such. One, we have mastering due tonight. Two, I moved the individual quiz to Friday because there is a strong possibility Barrie will be closed on Wednesday because of the weather forecast, because of the terrible, horrible ice storm. So, because Atlanta's already planning on shutting down. So Barrie has not officially said that they are closing. But in the strong possibility they will not be open on Wednesday. We're going to take the quiz on Friday. You may be thinking, no, I'm going to miss another 109 lecture. Don't worry. I'm going to pre-record the lecture, and you can watch it on your own time on Wednesday, and then we will just get started on Friday as though we didn't miss lecture. How awesome is that? That's what I figured, because we don't want to miss out on any more chemical equilibrium material. So my plan is to have that lecture posted hopefully tomorrow. I'm going to record tomorrow morning and post it. And so when I see you back here on Friday, we'll do the individual quiz and pick up wherever I left off on the video. Yes, ma'am?
Will the quiz cover that Wednesday?
It will not. No, the quiz will cover Friday and today. So the end of molecularity, and then today we're going to start chemical equilibrium. Yes.
Is class canceled for sure Wednesday?
No.
You're just going to do that for the next one?
I'm going to do that. They should tell us today if they're going to preemptively cancel. So if class is canceled, I will have the video recorded. If it doesn't cancel, then I'll just see here on Wednesday. And we'll do it anyway. Do it live. So I'm planning on it because it's supposed to be worse than 2 weeks ago. Because this is supposed to be a freezing rain and sleet and ice. Yeah. If class is canceled, I'll move the mastering from Wednesday to Friday. Yeah. All right, so let's get started talking. I'm letting you preview my notes. Okay. All right, so chapter 14 talks about equilibrium. So up until this point, everything we've talked about in chemistry has considered only things going forward, right? We always talk about reactants making products, and that's the only direction we consider. But in reality, all reactions can move in either direction, right? It's more appropriate to write it like this. Where there is a forward direction still, we can still go forward. But then there's also the reverse direction. Right, both directions are possible. We can go forward, we can go backwards. Reactions don't always go to completion, which means we don't go 100% forward. There's always some backward reaction. But lucky for you, we can make a prediction based on the likelihood of the reaction going forward or backward or being somewhere in between. So this whole chapter is going to be looking at how can we predict if the reaction is going to go forward to products, go reverse to reactants, or are we somewhere in the middle of those two options. So we call that states of equilibrium. So first, let's talk about rates. Like we just finished talking about rates, the first thing we're going to talk about is the rate of equilibrium. If I'm at true equilibrium, true equilibrium would have the rate of the forward reaction be equal and opposite to the rate of reverse reaction. That's the definition of equilibrium. As much is going forward as is going backwards. which means there is no net change in the concentrations of reactants and products. You've reached a point at which you're going to make as much product as you've made, and as much reactant is left over is going to be left over, and we're just switching back and forth between the two. Which, if there's no net change, that's called dynamic. Means that it's not stopped. So when the reaction is completed, it doesn't mean we're not making any more product. It just means you've made as much product as you're going to make. So when some switches back to reactants, well, then some of the reactants have to switch back to products. So we're still having chemistry happen. It's just there's no change in concentration at that point. All right, so dynamic means the reaction hasn't stopped. It's just we're not changing concentrations anymore. And all reactions will proceed to this point. They'll all get to equilibrium. The question is, how fast does that occur? And how can we make a prediction about that? All right, so let's take a look at some positions of equilibrium. That's a little better. All right, so I'm going to have 3 examples. So my first reaction I have sodium chloride solid being dissolved into sodium ions and chloride ions. How likely is sodium chloride to dissolve in water? Pretty likely, right? Pretty likely. So I think we could say at equilibrium, right, that'd be true that the concentration of sodium chlorides will be equal, but much, much greater than the amount of sodium chloride still left in its solid configuration. Just writing out in math what you just told me in words. So if that is true, which is the equilibrium arrow going to be more likely to be the one that goes towards products or the one that comes back towards reactants? Towards products. Which direction is that, left or right? So the book is going to go both ways. The reaction lies towards products, or it'll give you the direction of the arrow, like the reaction lies to the right or it lies to the left. So I would say the reaction is likely to proceed to products. Okay. Let's say I have this one. All right, so I have silver chloride that can break down into silver and chloride ions. From your vague recollection of when you took 108, is silver chloride likely to dissolve or not likely to dissolve? It is not. Silver chloride is our usual definition of not soluble. So this is still true. these two are equal. But which one of those two amounts is going to be in the greater, oh, no minus sign,
Solid.
the solid, right? The solid's going to be the greater component. So is this reaction likely to proceed to products, or is it likely to proceed towards reactants? Right, it sounds weird to proceed towards reactants, but it just means the equilibrium lies towards this way. All right, so those, oh yeah, question first, Paul.
Is there so obviously those two compounds that you gave us were pretty, I guess, basic.
Mm-hmm.
So is there a way to determine if they will?
The rest of the chapter, yeah.
Work?
Yeah, the rest of the chapter will help us make some awesome predictions. Yeah, ooh, and we're going to be able to use the quadratic equation. Hopefully everybody's ready. And then I'll show you a shortcut, so you don't have to use quadratic every time. All right, so then, you're right, here's my third example. All right, so let's say hydrogen and deuterium are floating around and somehow they combine to make 2HD. It's like 3D HD TV, but not really. Just kidding. So, right, so my third example is going to be the example where you can't really make a prediction. All right, because one's obviously one way, one's obviously the other way. The third one is, can't really tell.
Are the H2 and the D2s
Oh.
equal?
Yeah, that should be an equal, not a plus. There we go. So how do we make a prediction about equilibrium when we can't obviously, based on our knowledge of chemistry, make a good guess? We talk about the equilibrium constant. So kind of like you did in lab last week, right? You had equilibriums that you looked at, and you had some equations that you omitted solids and pure liquids, right? Okay. So the equilibrium constant requires us to look at elementary steps of a reaction. So let's say, for example, I have this. I'll come back and fill in some stuff over here. Those are G's. They're not very good-looking G's. All right, so I have iron and carbon monoxide making an iron-carbon monoxide crazy combination. I just picked some random chemicals. This will probably never actually happen. You can't really have gaseous iron. But I thought it'd be a good example where we have no idea how to predict this, all right, because no one's ever worked with gaseous iron. I don't think. I mean, maybe they have. All right, so if I looked at the elementary step, and I looked at the rate forward, so like we did on Friday, we only looked at the reactants, but the stoichiometric coefficients are the exponents. Right, so that's how I would write the elementary step for the forward portion of it. I have 1 iron, 2 carbon monoxides, so that'd be true as its elementary step. also write an elementary step if I was going the other direction, right? If I wanted to go products back to reactants. All right, so at equilibrium, what did I say about these rates? They are equal, which means I can now set them equal. I'm going to put an F and an R next to those Ks, because they should be different Ks, just to keep them separate. All right, so now I have a mathematical equation. What do we do when we see crazy mathematical equations like this? Usually the first step. Get the like terms on one side or the other, right? So I'm going to get all the K's on the left and all the brackets on the right. All right, so just rearranging the terms. Everybody see what I did? Nothing too tricky. Product. I now have a combination of rates that's equal to the concentration of products over the concentration of reactants raised to the power of their stoichiometric coefficient. We're going to call that equal to, you're going to want this K to look different than all the other Ks. It should be a capital K. I'm going to put little hats on the edges of it so you know that's a big K. So big K, which is the equilibrium constant. And so that big K will be the equilibrium constant for this reaction. As long as we have a given temperature, right? Because we talked about how rates, the Arrhenius equation tells us that rates are temperature dependent. And so if I looked at this reaction at 25 degrees, it may make a little bit of product, but if I heat it up, it may make more product. So we have to be careful that we're looking at forward and backward at the same temperature. So that means we now have a generic equation. So if that's my generic reaction, right, I have some amount of A plus some amount of B makes some amount of C, okay? That's now our generic equation for the equilibrium constant for any balanced chemical equation at a known temperature. Why does it matter if there was a balanced chemical equation or not? It's raised to a stoichiometric coefficients. So if you don't have the balance, if you don't have the equation balanced before you get started, you'll have all the wrong exponents. So from here on out, you're going to want to be very careful about, did Dr. Sorovic give me a balanced chemical equation? Most of the time I will. There is a slim chance, I'm not going to test, that it may not be balanced. And you'll want to make sure you check that before we go on to the next steps. Okay, how do we feel about that? Good? Questions on that? Yeah.
So K, the equilibrium constant, is just K forward divided by K
Reversed. Yep. Yep. All right, so what does that big K mean? Right, how can I make a prediction knowing big K? Well, it means this. if we have a large value of K, it means that it is more likely to make products. So let's take a look at an equation, see why that might be true. All right, so let's say I have 2 ozones that can decompose into 3 oxygens. Which one is more stable, ozone or oxygen? Oxygen's more stable, so which way would we predict this reaction to go? Towards products or towards reactants? Right, we expect it to go towards products. So let's write out what K would equal. So, right, we got a fraction. So does the oxygen or ozone go on top? Oxygen goes on top, yeah, because it's products. And then what do I raise that to? 3, okay. So then this goes on the bottom. All right. Now it turns out I happen to have looked this up. K for this reaction is 2.54 times 10 to the 12th. I would say that counts as large, right? Large number. So when we say large, large is going to be greater than 1. Not 1, but anything greater than 1. And the farther away you are from 1, the more likely it is to go towards products. So it's kind of a gauge, right? So this is really far away from 1, which means this is really, really, really only going to make products. There's very small chance that it will come back and make reactants. What else do you notice about my K over here? Maybe like, where's those units at? If you're thinking at all, units, right? Well, K is, right, big K is K over K. The units will have canceled. So big K is unitless, always. So make yourself a little note down here, big K. No. This is the one time where if you forget units, it actually works in your favor. There are no units. All right, so then let's look at small values of K. So if my large is greater than 1, what do you think my small has to be? Less than 1, okay. All right, let's look at another, let's do this one. Let's say I have chlorine gas spontaneously breaking apart into elemental chlorine. How likely does that seem to happen based on your knowledge of chemistry? Pretty much will never happen, right? So let's write out the equilibrium constant. So of my 2 options, the chlorine, the reactants or products, which one goes on top? Right, products goes on top, and what do I raise it to? 2, okay. Good there, good. Well, this happens to equal 1.4 times 10 to the negative 38th. So that is a measure of how likely you are to make elemental chlorine out of chlorine gas. You can always think about it as a probability. Right? Probability greater than 1 is very likely to happen. Probability less than 1 is never going to happen. So would you say, I guess I already have it up here. So this is reactant favored. How do you feel about that? Good as a measuring stick. All right, so that's good. We have values greater than 1, values less than 1. What if we're at 1? We'll come to it. We'll have to determine the extent of reaction. And so we'll do that in a few minutes. So if K is real close to 1, we'll have to do some other things to figure it out. Probably should have done the previous slide. All right, so let's talk about this reaction quotient, right? So we have big K, which is the equilibrium constant, which by definition means you have to be at what point of the reaction? Equilibrium. What if you're not sure you're at equilibrium? All right, so K, by definition, reaction is at equilibrium. What if you don't know if you're at equilibrium or not? We're going to use this reaction quotient to tell us if we are or not. All right, so let's say I have generic reaction. There should be arrows. I'll have a very generic equation. A going to B. Let's say I'm at equilibrium. I can use my big K. Which letter goes in the numerator? The A's or the B's? Right? B, and I raise it to what power? B. Yep. So then I have to put A to the A down here, right? Just like we've had a bunch of times now. All right, well, we can define a similar thing for any point in the reaction, right? So K is at one specific time, right? The reaction has gone on long enough that we know we're at equilibrium. But maybe you're at the very beginning, or maybe you've been there 20 hours, you're like, maybe we're at equilibrium. We're going to use big Q, but it's going to be defined the exact same way. Because big K tells us, by definition, you're at equilibrium. Q just means maybe we're at equilibrium, maybe we're not. We'll compare the two and see who we're at. Where would you guess you are in the reaction of K equals Q, value-wise? We are at equilibrium. All right, that should make sense. So we'll figure out Q. If Q equals K, definitely we're at equilibrium. Okay. All right, so let's say we have a Q value greater than our known K value. It means, right, based on this fraction, if this fraction is bigger than this fraction, the numerator must be big. Does that make sense? It means I have more of this than I do that, so this fraction is bigger than this fraction. So it means that there is more more product than there would be at equilibrium. So if there's more product than there should be at equilibrium, which way should the reaction go to balance it out? Make more product or make some reactants? It should go back towards reactants. So we'll say reaction should shift left, which means follow the arrow back to the reactants. That makes sense? If Q is big, it means that the numerator is big. So if that numerator is big, it means we got to bring it down. We'll do that by making more reactants. Okay, let's look at the opposite case. I mean, there's only 3 options, right? So now if I have Q less than K, what do I have too much of? I have too much A. All right, means there's too much A. So which way should my reaction shift to fix that problem? Towards products, which means it will shift right. All right, so why don't we do a practice problem and see how that actually plays out. So I know I have this reaction, which is totally not balanced. That should be a 2 there. There we go. All right, so I have 2 nitrogen dioxides that will make 1 dinitrogen tetroxide. I also teach 108, and right now we just finished naming, so I'm all over my naming compounds. All right, so let's say I know that the equilibrium constant for this reaction is 170. If I know some other things about this reaction, we have to figure out if we are at K or not. And then what do I need to do to reach equilibrium? So let's say for this reaction, I know we have that's a 4. All right, so let's say I know those concentrations of each of those. So I need to figure out Q and figure out how Q is related to K and then make a prediction. So which one of these 2 compounds goes on top, the N2O4 or the NO2? Okay, N2O4. So, and then what do I need to do to this NO2? I need to square it. So we can plug in what we have. If you don't have your calculator out, you should probably fish it out because we're about to do some massive calculating here in a few minutes. 1.5 e to the 4 divided by 2.0 over 6 squared. I understand sig figs will make this look a little crazy. It should really be 38. I didn't give you enough decimal points. All right, so 1, we've calculated Q. 2, are Q and K equal? No, right? K is 170. Q, I just figured out, is 3,800. Are they even close? Not really. Is Q greater than or less than K? K. Q is greater than K. Good. If you need to draw a number line, you could do that. All right, so if Q is greater than K, it means there's more products. All right. So what do I need to do? Do I need to make even more products, or do I need to start making some reactants? Okay. So which way do I need to shift it? Shift it to the left or to the right? Okay. Reaction needs to shift to the left. It needs to make more reactants. Good. How we do one more? All right, so given K and the concentrations, take a minute and figure out, are we at equilibrium? Does Q equal K? And if not, which way do we need to shift our reaction so that they would be equal? Something like 10.8 or so. Anybody not get 10.8? All right, is Q equal to K? Is Q greater than or less than K? Less than. So if Q is less than K, do I need more products or more reactants? I need more products. So which way will this shift? Shift right. Okay. So those are going to be the kind of questions it's going to ask, right? It's not going to ask you for all the steps. It's just going to say, are you at equilibrium? And what's going to be the shift? Which means you have to do all the steps. But it's not going to ask for all the steps. How are you feeling? Confident? Okay. Let's then talk about what happens when we are not at equilibrium and we're not exactly sure where we are in this reaction. In reality, halfway through the reaction, do you have any idea what the concentrations are in there of all the reactants and all the products? Halfway through. Do you have any idea what's going on? Right. You know at the beginning, right? You know how much you put in there. And you probably at the end will know how much, which is why this Q idea is kind of weird, because there's very unlikely halfway through the reaction you can stop it, figure out the concentrations of everybody, and be like, oh, I am at equilibrium or not. not experimentally practical. Right, so the only way you can determine K is if you know you are at equilibrium. But you don't always have all those other options. But you do have the balanced chemical reaction. 3 exclamation points, that's how excited you should be. Balanced chemical reaction. So if you know the initial concentration and you know the balanced chemical reaction, we can make some amazing predictions about what will be the concentrations of everybody at equilibrium. So this is my favorite part of the chapter. I'm very excited. We get to do ice tables. Yay. Okay. I look forward to teaching 109 every year so I can do ice tables. All right, so let's say, for example, I have butane interconverting with isobutane, and I know that the equilibrium constant for this reaction is 2.5. Ooh, that's not spelled right. That should be mole, not moel. The question is, I know the initial concentrations. I don't know what those concentrations will be at equilibrium. So let's start off by determining some things about the system. So this is what the structures are. It tells you that it interconverts. So it's 1 to 1. Butane goes to isobutane, back to butane, back and forth, back and forth, back and forth. I'll write this over here. Try to be tricky. What is going to be the concentration of butane if I know moles and milliliters? It's the only tricky thing I put in this question. All right. All right, something like that. Okay, so I know the initial molarity of butane. I'm going to abbreviate that I for initial. Good so far. So initially, I put in 0.34 molar of that, right? If I have a flask and it says I have those things in it, I'm going to put in 0.34 molar. Did the problem tell you anything about how much isobutane I put in there initially? So it's assumed to be 0. C, the C row is going to be called change. So we can make a prediction about what the change in concentrations will be based on my balanced chemical equation. Am I gaining or losing butane as the reaction proceeds? Right, you expect it to lose, right? Because I need to make some of this. So I'm going to call that minus X. I've lost some amount as the reaction goes on. What would you guess how much isobutane I'm going to make? Plus X. Mm-hmm. Right, so whatever this loses, this one has to gain. Which means at equilibrium, which is the letter E, that must be true, and that must be true. So initially I have 0.34. As time goes on, I lose some amount X, which means at equilibrium I have 0.34 minus X. Initially I have 0. I gain some amount X, which means at some point I have 0 plus X. Just X, fine. All right, so this is where we're going to get into some not complicated at all math. Just some rearranging. Well, I'll probably have to save the quadratic equation for next time. I know. If you want to work ahead, we can do that. Okay, so I know K, right? I know K for this reaction.
I told you
is up here is 2.5. All right, if I was going to write out the K equation for this, does the isobutane or butane
go on top.
isobutane? And I already know
The concentration, it's right
there,
there.
it's X. All right, so then
Butane goes on
on the
the
bottom, and I know what that is. It's
0.3.
4 minus X.
All right, so look at that.
I now have one variable,
That I can solve for everything.
things in terms of X. So what would you like
To do as your first
step to solve for X by itself? Yes.
Do you always want to use some change then when putting it into the initial?
Never use the initial, always use,
use equilibrium.
yep, because K is defined as the equilibrium constant,
So we have to use the equilibrium.
because change will not
Always be this
nice, as we will see soon. Okay, so we'll do something like this, right? If your numerical rearranging skills need a little,
tuning up.
I would take a little refresher before we get too far into this chapter.
All right, so then I can,
Multiply out what's in this little parentheses.
let's see, so I got 2.5.
5 times 0.4. All right, so then
What do I need to do to get
the x's all onto one side. All right, I add that. All right, so then what's my last step to get the x all by itself?
divide?
So then 0.85 divided by 3.5.
It will be molar, but
We're
we're not
not done. So, right, we had this table
at the top.
So x just tells me what the change was,
It doesn't tell me.
what the final equilibrium is. So in order to figure out butane, I have to do 0.34 minus 0.24.
So at equilibrium,
The butane concentration is 0.1 molar. And it happens to be in this case
that isobutane is.
x. So it is 0.24 molar. All right, how do you feel about that? Pretty good. Super confused. Perfect. We will do a
Bunch more.
either on the video or if I see you on Wednesday.
We'll work
Do a bunch more of these.